We already know how to add vectors and how to perform the dot product with vectors. So this video is going to introduce us to another operation with vectors called the cross product. In the cross product, we are taking two vectors, A and B, and we say that we cross those vectors, so A cross B, and our resultant ends up being a vector. That's different from the dot product, which we previously learned, where when we do A dot B, our resultant is simply a scalar. Another name for the cross product is also the vector product. We can find the magnitude of the cross product by multiplying the magnitude of each vector, A times B, times the sine of the angle between vectors A and B when they're placed tail to tail. This only gives us the magnitude, and since the resultant is a vector, we also need to find the direction. To do so, we use a version of the right-hand rule, which means we're using our right hand, where our thumb, first finger, and either middle finger, or you can use all three fingers together, are all at right angles with each other, which you can see a little bit from this diagram here. When we are using this right-hand rule for the cross product, our thumb always represents the first vector, our pointer finger always represents the second vector, and then our three fingers, or perhaps just our middle finger like you see in this diagram, represents the result, which I've called vector C, or you could say that it represents A cross B. We'll do some examples in class where we are using this equation for magnitude and the cross product to come up with the direction. But we can also determine the cross product when we have vectors that are in unit vector notation. To do that, we're going to use a matrix. Let's look at an example for that. I want to take the cross product of these two vectors. Vector A is equal to AI hat plus BJ hat plus CK hat, where A, B, and C would likely be numbers, though they could also be variables or expressions. And then you'll see my vector B is very similar, but it's XI hat plus YJ hat plus ZK hat. Once again, X, Y, and Z could be numbers or could be expressions. So we're going to create a matrix from these two vectors. Our matrix has as its top row the symbols I, J, and K, and that'll always be the case. The second row of our matrix are the variables, or sometimes, as I mentioned, could be constants, that are in front of the I hat, J hat, and K hat on your first vector. So A, B, and C in this case. And then our last row are those coefficients, those things in front of the I hat, J hat, and K hat on your second vector. It's really important to the order that we have of these so that your second row is always the first vector of your cross product, and your final row is that second vector on the cross product. What we're going to do with this matrix is actually find something called this determinant. I'm going to show you one method of doing that, but there's plenty of other ways you could find from math textbooks of finding the determinant of a matrix. We symbolize finding the determinant by putting straight lines on either side of our matrix. And the method that we're going to use requires us to rewrite the first two columns to the right of our matrix. So I hat A X and J hat B Y. That's the first step in finding this determinant. Then what we're going to do is we're going to multiply across diagonals. So I am going to multiply I hat times B times Z, J hat times C times X, and K hat times A times Y. I'm going to add together what I get when I multiply those. So in other words, I have B, Z, I hat. We always put our unit vectors last when we're expressing things. Plus C, X, J hat, plus A, Y, K hat. That's the first part here. Then I'm going to subtract what I get when I go the other way with my diagonals. In other words, My three diagonals are going to look like that. So bx k hat plus cy I hat plus a z j hat. If I actually had numbers in here, I would then multiply those numbers out and combine like terms so that in the end, my resultant would just have something times I hat plus something times j hat plus something times k hat. We'll, of course, apply this to several physics scenarios throughout the year.